In this video, we're going to be talking about seismic waves. So, seismic waves typically occur in the lithosphere and they're caused by the movement of tectonic plates. So, there are multiple parts when it comes to an earthquake. The point where the earthquake mainly originates from is called the focus. Directly above at the surface is called the epicenter. This line over here is the fault line, which is the boundary between those two tectonic plates. And the round circles that we see over here are those seismic waves that are happening. Now, the difference between body waves and surface waves are that body waves mainly travel around the interior of the Earth's surface. Meanwhile, surface waves, as the name suggests, happens only at the surface of the Earth. So the surface waves is the ones that cause the most destruction, and body waves are the ones that travel across the entire Earth. So now let's move to P waves. P waves are longitudinal waves. We saw in the previous video with longitudinal waves that they can have rarefaction and compressions. Now, these rarefactions and compressions is what creates these longitudinal waves. So P waves are the fastest amongst all these other waves, and they're able to travel through solid and liquid. If we were to take an entire anatomy of the Earth, let's say this point over here is where the P wave started. The thing about the P wave is that it is able to move across the entire Earth, and because the outer core has a liquid, the outer core is mainly liquid with a liquid iron and liquid nickel. Since it's able to travel through solid and liquid, what's happening is that it's able to change its trajectory. Now, this can happen in multiple ways. It can either reflect off, it can get absorbed, it can refract, like changing angle, and it can transmit through it. So over here and over here, they reflect and can go to a different location. For refract, we can see that it's going in this location, but then it changes angle over here. That's a refraction. And then transmission is transmitting through the entire part over here. So it's going through multiple different densities, but it's able to still go through the other side of the Earth. We also have these gaps over here, and this is mainly because the reflected parts aren't hitting these areas at all. So because of that, these are called P wave shadow zones. So they don't get any of the seismic activity, and that's what enables scientists to be able to calculate the P waves most efficiently. Next, so let me create a quick demo of P waves. Since P waves are longitudinal waves and have rarefactions and compressions, it looks something like this. When watching, you can mainly see the compression here, but a lot of the rarefaction like here. That's how a P wave is able to move through the Earth. Now let's move on to an S wave. S waves are not longitudinal waves, but rather they're transverse waves, meaning they don't have rarefactions and compressions, and each part has a same wavelength. So the thing about S waves is that they're not able to travel through liquids. They're only able to travel through solids. S waves stand for secondary waves. So because they're secondary waves, they come after the P waves. S waves are much more slower, and they also originate at the focus point, or where all the seismic activity was originated from. And since the S waves are only able to move through solids, they don't move through the liquid outer core. Instead, they only come to here. And now the thing is that we have this humongous S wave shadow zone. We talked about the P wave shadow zone because of the reflection, it's not able to move through. But here, since it's not able to go through the liquid, this entire part over here does not get those seismic activity. So S waves have a crest, which is the top over here, and the trough, which is the bottom over here, and the wavelength is the same compared to longitudinal waves. I'm going to be demonstrating an S wave right now. So we can see how it was going up and then coming down and going up and coming down. This is a perpendicular motion. So alright, now let's move to L waves. They move horizontal or perpendicular to the line of propagation. So propagation is this line over here. It's a straight line. Now the thing about the straight line is, as it's crossing through, it's either going left or it's going right. So because of that, and it's also happening very sudden, we can see that over here, there's more action, over here there's more action, over here there's more action, but then over here there's less action. So we can tell that it's a very sudden change. So if I were to display this on a slinky, it would happen like this. So it happens at the surface, so that's why we get that shaking all of a sudden, like it's sudden shaking. So that's what's mainly causing it. It's kind of like an S wave, but except it's much more sudden, as we can see over here, more concentrated areas of sudden movement, but then areas where it's not that concentrated in sudden movement. So it goes like this. And you can also tell it's having that horizontal or perpendicular shifting. And lastly, we have R waves. R waves create this elliptical or retrograde motion. So this over here is the line of propagation. And the thing about R waves is as it's moving up and down, let's take this red dot for example. It's moving up, but then it's coming down, moving up and coming down. You can understand it better through the example I'm going to show. However, we can see over here this retrograde motion. If the particle of the wave was here, it's coming up, but then eventually it's going to come down and come up and come down. So that's the thing about Rayleigh wave. It's the particles staying in the same position. It's basically staying in the same position, but it's moving in an elliptical orbit around the line of propagation. So if I were to display that, it would happen like this. That's why we get that jumpy feeling when there's an earthquake. You see that when I lifted it, the particle went up, but then when it passed, it went down. And if I were to continue it, like it went up, but then the energy transferred and the particle went back down. So it's creating that elliptical orbit. L waves are slower than P waves and S waves, but are faster than R waves. R waves are the most slowest. The difference between love waves and R waves are that R waves move in an elliptical or retrograde motion, while L waves move in a horizontal or perpendicular motion in relation to the line of propagation. This is all about seismic waves.